Alright, so we are going to be working in section 4.4 today. So this is going to deal with shape of the graph, specifically something called concavity, which is sort of if a graph's opening up or if a graph's opening down. So we have this idea of concave up. And this is, if your graph has kind of a shape where it's opening upwards, or you could maybe have half of this shape, something like that, where it kind of opens up, or like just the other half. These are all shapes that we would consider concave up. Concave down would be a graph that opens downwards, so the opening is kind of down here. You could have kind of half of that graph, and we could still consider that concave down, or the other half, and we would consider that concave down. So to kind of see a way to determine concave up and concave down, let's draw a concave up graph, and let's look at the slope of the tangent lines a couple places. So if we take the tangent line here, we would see that your tangent line has negative slope. Down here we would see it's less negative. Over here it's slightly positive. It's still kind of close to horizontal. And then as we move on, the slope gets steeper. So we went from kind of steep and negative to less negative. Somewhere in here it's actually 0. Then it's slightly positive. Then it's really positive. So if we look at this, the tangent lines go from big negatives to little negatives to 0 to little positives to large positives. So we could note the slope of the tangent lines are increasing. And we can probably guess if, well, the slope of the tangent lines when you're concave up, if the slope of the tangent lines are increasing, then when you're concave down, we would maybe expect the opposite to happen. And we'll just kind of verify that it does. So we start out very steep and positive. We get less steep, still positive. We become 0. We start to get slightly steep again, but we're negative. Then we get really steep and we're negative. So we go from large positive to less large positive to 0 to slight negative to very large negative. And so we can see the slope of the tangent lines are decreasing. So we're going to kind of put this together in some terminology here, and we're going to define what we mean by concavity. We're going to look at an example from the book. Then we're going to put down some concavity tests and something called point of inflection. So we're going to define concavity. So we're going to let f of x be a differentiable function. On an open interval a to b. Then the following things happen. We say the base graph f, or the starting graph f, is concave up on the interval a to b if f of x is increasing on that interval. And we just kind of saw, well, the slope of the tangent lines are increasing. If you remember, the first derivative is the slope of the tangent lines. Whoops, should say f prime of x is increasing. So this right here, the slope of the tangent lines, that is f prime. The slope of tangent lines is f prime. So basically, we say if f prime is increasing, we're concave up. If f prime is decreasing on part of an interval, we're going to be concave down. So we'll say F is concave down. On, try to make that slightly better, on A to B, if f prime of x is decreasing on that interval A to B. Okay. So now we're going to do a example, and we'll take a look at that. This will be example 1. And we have we're going to look at the stocks of two companies. We call them A and B. So we have company A and company B. They both currently sell at $75. One is a better estimate, or better investment, I think. And they want us to explain in terms of concavity. So our two graphs that they give us, they say, all right, graph A starts here at 25, and then out here where you're thinking of buying it, the price is 75, and its shape looks kind of 25 out to 75. So it looks like this. So this is time, and this is stock price. So graph of B starts at the same point, 25. It's selling for 75 right now. We're at the same time. Let's say that time is, I guess we'll just call it T. So at time T, we'll get her up here, and this one's graph curves the other way. And this is graph B. And we can kind of see, based on these two graphs, we can say A is concave down, B is concave up. And if we look back to our definition, if you're concave up, f prime is increasing. If you're concave down, f prime is decreasing. So we're concave down, which tells me that the rate of change of the stock, the first derivative, is decreasing. So we're concave down, so f prime is decreasing. We're concave up over here, so f prime of x is increasing. F prime of x, in this picture, this represents the instantaneous rate of change. Of the stock price with respect to time. We want that value to be increasing, so this says graph B will be the better choice. Or company B, I guess, is better. And the reason for that, if you look at the instantaneous rate of change, which kind of predicts how the stock is going to be moving, this one, it's flattening out, so your change is approaching 0. So the tangent line slope approaches 0. Which means that the rate of change that the stock moves is stopping. So if we extend it a little bit, if we extend it by a delta x, the slope of the tangent line can kind of predict where the next point's going to fall. And the next point's probably going to fall kind of horizontal of this point if your tangent line slope's doing that. On this one, the tangent line slope is like this. So it's a steep, positive tangent line slope, or slope of tangent line, I guess we could say. So what that means is if we use that to predict where the next point's going to fall, the next point's going to fall kind of up here, which means the stock is increasing in value. And if this one continues to be concave down, eventually what's going to happen is if this continues concave down, the graph will turn around like that eventually, so you'll start losing value. If this one continues to be concave up, the graph will continue to increase at an increasing rate, and that means you would make more money. Okay, so that's basically a bit about concavity and kind of how it relates to the first derivative. So we'll stop this part 1 here.